Hi, this is my GEOL0069 end-of-year assignment. My project is called a lightweight geohazard mapping pipeline for landslide detection using Sentinel-2, DEM, and machine learning. The main aim of this project is to build a small but complete AI for Earth observation workflow for landslide detection. Instead of training a very large deep learning model, I wanted to create a lightweight and interpretable pipeline that combines satellite imagery, terrain information, and machine learning. The final output is a landslide prediction mask, together with model evaluation, feature importance, and an environmental cost assessment. Landslides are important geohazards because they can damage roads, buildings, pipelines, and other infrastructure. They can also be triggered or made worse by heavy rainfall, earthquakes, and rapid land use change. Traditional landslide mapping often depends on field surveys or manual image interpretation. These approaches can be accurate, but they can also be slow, dangerous, and difficult to apply quickly over a large area. This is where Earth observation and machine learning can help. Satellite imagery allows us to observe large and inaccessible areas, while machine learning can combine different types of information to identify possible landslide-affected pixels. For this project, I used the Landslide 4sense dataset. This dataset is suitable for this assignment because it already combines Sentinel-2 multispectral bands, DEM-derived terrain information, and pixel-level landslide masks. Each image patch contains 14 bands. The first 12 bands are Sentinel-2 bands, and the final 2 layers are slope and DEM. The mask is a binary label, where 0 means non-landslide and 1 means landslide. Because the full dataset is quite large, I used a smaller subset for this course-scale project. This also reduces storage and computational cost. Here is the overall workflow. First, I load the image and mask files from the dataset. Then I visualize the input data, including RGB, false color imagery, DEM, slope, and the ground truth landslide mask. After that, I calculate several spectral indices, including NDVI, NBR, NDWI, and BSI. These indices are useful because landslides often remove vegetation and expose bare soil or rock. Then I combine the original bands, terrain data, and spectral indices into one feature stack. After that, I use balanced pixel sampling, train a random forest classifier, predict landslide masks on unseen test patches, and evaluate the model using precision, recall, F1 score, and IOU. Finally, I tune the landslide probability threshold to reduce false positives. In the notebook, the first part sets up the Google Colab environment and connects to Google Drive. I define the project folders for data, outputs, figures, metrics, and documents. Then I install and import the main Python packages, including NumPy, Pandas, Matplotlib, H5py, and scikit-learn. The next part downloads and extracts the Landslide 4sense training data. I only extract a smaller subset rather than storing the full raw dataset in the GitHub repository. The raw H5 files are not uploaded to GitHub because they are too large. Instead, the notebook explains how to download and extract the data, and the repository only includes the code, figures, metrics, and documentation. After loading the data, I visualize one example patch. In this figure, the first panel is the RGB composite, which shows the optical satellite view. The second panel is a SWIR, NIR, red false color image, which helps highlight surface and vegetation differences. The third and fourth panels show DEM and slope. The final panel is the ground truth landslide mask. This step is important because it checks that the dataset has been read correctly and that the image and label match. Then I calculate 4 spectral indices. NDVI is used to represent vegetation condition. NBR is useful for surface disturbance and bare ground. NDWI represents moisture and water-related effects. BSI is the bare soil index, which is especially relevant because landslides often expose fresh soil or rock. These indices are added to the original 14 bands, so the model has both spectral and terrain information. For the machine learning model, I used a random forest classifier. I chose random forest because it is lightweight, fast to train, and interpretable. It also gives feature importance, which is useful for understanding what the model is relying on. This is suitable for this assignment because the project is not just about getting a prediction, but also explaining the AI workflow and its implementation. One problem with landslide detection is class imbalance. Most pixels are non-landslide, while landslide pixels are much rarer. If I train the model directly on all pixels, it might learn to predict non-landslide most of the time. To reduce this problem, I used balanced pixel sampling. For each training patch, I sampled landslide pixels and a controlled number of non-landslide pixels. This gives the model a better chance to learn the difference between the two classes. The model was evaluated on held-out patches that were not used for training. This is important because pixels from the same patch are spatially similar. If pixels from the same patch were mixed randomly into both training and testing, the score could become too optimistic, so I split the data at patch level instead. The feature importance plot shows that the model relies strongly on BSI, NBR, NDVI, and some visible and SWIR bands. This makes sense physically because landslides are often associated with vegetation loss, bare soil, and surface disturbance. This suggests that the model is using meaningful remote sensing information rather than just random patterns. The default random forest model used the standard classification threshold. At this stage, the model had a precision of about 0.373, a recall of about 0.900, an F1 score of about 0.527, and an IOU of about 0.358. This means the model detected most landslide pixels, so recall was high. However, precision was lower, meaning that the model also produced quite a few false positives. In other words, the default model was good as a rapid screening tool, but it overpredicted landslide areas. This can also be seen in the prediction examples. Some true landslide areas are detected, but the default model also predicts many extra landslide pixels in non-landslide areas. This is a common issue because landslides can look spectrally similar to other bare or disturbed surfaces, such as exposed soil, rock, river channels, or shadowed terrain. To improve this, I added a probability threshold tuning step. Instead of directly using the default class prediction, I used the random forest probability for the landslide class and tested several thresholds: 0.50, 0.60, 0.70, 0.80, and 0.90. The threshold tuning figure shows the trade-off clearly. As the threshold increases, precision improves because the model becomes more conservative. At the same time, recall decreases because some true landslide pixels are missed. In this experiment, a threshold of 0.90 gave the best F1 score and IOU. Using the 0.90 threshold, the final performance improved to a precision of about 0.703, a recall of about 0.617, an F1 score of about 0.657, and an IOU of about 0.490. This means the final model is more conservative than the default version. It misses some landslide pixels, but it produces fewer false positives and gives a cleaner, high-confidence landslide mask. The final threshold-adjusted prediction examples show this improvement. Compared with the default prediction, the output is cleaner and less noisy. This demonstrates why threshold selection is important in geohazard mapping. If the goal is emergency screening, a lower threshold may be useful because it captures more possible landslides. If the goal is a cleaner inventory-style map, a higher threshold may be better because it reduces false detections. There are still several limitations. First, this project uses benchmark image patches rather than one continuous georeferenced landslide event, so it is not yet a full operational WebGIS product. Second, the model is based on optical imagery, so cloud, shadow, vegetation cover, and image quality can affect the result. Third, random forest treats pixels mainly as feature vectors, so it does not fully learn spatial shape or landslide morphology in the same way as a CNN or UNet segmentation model. Finally, the model was trained on a subset of the data to keep the project lightweight, so a larger dataset may improve generalization. For the environmental cost assessment, the project deliberately uses a lightweight model rather than a large deep learning architecture. Random forest trains quickly and does not require long GPU training. The notebook also uses a smaller subset of the dataset and saves intermediate outputs, which reduces repeated computation. This keeps the environmental cost low compared with training a large CNN or foundation model. However, if this workflow were scaled to national or global landslide monitoring, the computational and storage demands would increase. Overall, this project demonstrates a complete AI for Earth observation workflow for geohazard mapping. It combines Sentinel-2 bands, DEM, slope, and spectral indices with a random forest classifier to detect landslide-affected pixels. The project also includes model evaluation, threshold tuning, feature importance, a documented GitHub repository, and an environmental cost assessment. The result is not a fully automatic operational landslide inventory, but it shows how a lightweight and interpretable machine learning pipeline can support rapid landslide screening and geohazard analysis.